Computational thinking is a fundamental cognitive skill that involves solving problems systematically and logically, similar to how a computer would approach a problem. This skill is based on four key phases: breaking down complex problems into smaller parts, identifying recurring patterns, applying abstraction, and designing algorithms to solve them. Let's explore each of these phases in detail. The decomposition phase consists of breaking down a complex problem into smaller, more manageable problems. This simplifies the overall problem and makes it easier to tackle. Similarly, when we divide problems into smaller structures, they become easier to understand and solve. To better understand this process, let's analyze a concrete example based on designing a smart alarm system to protect a house. In this phase, the project will be broken down into smaller problems, focusing on identifying key components and necessary functions. Key components may include motion sensors, door and window opening sensors, a siren, and a control panel to activate or deactivate the alarm using a code. As for the necessary functions, we might consider critical aspects such as intrusion detection and the activation or deactivation of the alarm. This decomposition allows us to analyze and address each element in a more specific and detailed way, laying the groundwork for efficient design and implementation of the alarm system. Once we have broken down the problem into smaller parts, it is essential to look for patterns or similarities among them. This process involves identifying repetitions or regularities that enable us to find common solutions to address different aspects of the problem. By doing so, we can discover strategies and approaches applicable to multiple facets of the issue. In the context of designing a home alarm system, we could identify common intrusion patterns in houses to determine when and how incidents typically occur. For example, we might ask whether burglars usually enter through the door, the window, or the chimney. Here, we are in the pattern identification phase, observing trends and recurring behaviors. After identifying home intrusion patterns, we move on to the abstraction phase. In this step, we ask ourselves what is truly relevant to creating a secure alarm system without getting caught up in unnecessary details. For example, we generalize intrusion patterns to decide where to install the sensors effectively, focusing only on critical areas and avoiding unnecessary installations. Additionally, we can evaluate which types of sensors are most suitable for the different intrusion patterns considered. We can abstract the idea of using opening sensors for doors and windows and motion sensors for areas like the chimney. Abstraction allows us to focus on the essential aspects, leaving out non-essential details. This approach not only minimizes resource usage, but also maximizes the effectiveness of our alarm system against intrusions. Now we move on to algorithm design. In this phase, we create an ordered sequence of steps to solve each part of the problem. These steps must be clear, logical, and repeatable. Following the alarm system example, at this stage, we develop a simple algorithm where if movement is detected, the alarm sounds. We could also implement more complex algorithms, such as a 20-second timer that allows homeowners to enter a deactivation code after the alarm is triggered. Or we could integrate a notification function that sends alerts to homeowners or a security company when an intrusion is detected. Learning computational thinking is valuable not only in the world of technology, but also for developing cognitive and problem-solving skills applicable to a wide range of situations, preparing students for the future. It is like a bridge connecting two worlds. Computational thinking is the link between our tangible world and the world of technology. Computational thinking helps us break down complex problems into smaller, more manageable parts, making them easier to solve. It also helps us evaluate different options and select the best solution based on specific criteria. Computational thinking fosters creativity by enabling the development of innovative solutions through algorithms and programs. It also includes communication and teamwork skills, facilitating effective collaboration in interdisciplinary projects. Computational thinking is applicable in a wide range of situations and contexts, meaning that the skills acquired are transferable and useful in various aspects of life. Finally, it is crucial to understand that computational thinking is not limited to programming or computer science, although these fields make extensive use of it. Programming is a practical manifestation of computational thinking. involving writing code in a programming language to create programs that perform specific tasks. When we program, we apply computational thinking to design algorithms that solve concrete problems. Thus, while computational thinking is a set of mental skills that includes abstraction and problem solving, programming is the practical implementation of these skills to create software.